So when we now look at these type of contractions, what we see here is that we need to interchange the position in order to bring two operators together, because we are looking at an expectation value. Then we need to interchange alpha 1 with alpha 2, so that then when we do this interchange, then we can either change that one, so we can interchange these two operators, and that gives rise to a minus sign. And that means that we will get a matrix element or contribution, which is going to have a minus. So we keep alpha 1 and alpha 2 in the same position here. But then in this particular case, we get alpha 2 and alpha 1 because we have interchanged alpha 2 and alpha 1. Then what I can do next, I can do the next contraction, but where I now change these guys. Oops. So I can do this contraction here, and then I keep the contraction which I did here. So let's do that. So what I will get then is an additional minus sign because I'm interchanging these two operators. So that gives me, every time you're interchanging, remember now that when you use the anti-commutation rules on that one, or this one, to bring two operators close to each other, the anti-commutation rules just give you a minus sign. So that means that I get a minus sign from here, and I get a minus sign from here. And that element is going to look like alpha 2, alpha 1, or V, alpha 2, alpha 1. And what we know, due to the symmetry of the operator V, then due to that symmetry, this integral here is the same as that integral. So I get two terms which are the same, and we have a factor of a half in front. So when we're adding up these contractions which are non-zero, we get rid of the factor of a half. And then it shouldn't come as a surprise that if I now stick with the last one, which I keep like this, like that one, but then I go back to the original left-hand side. This is going to give me a minus sign. So that will give me a minus alpha 2, alpha 1, or V, alpha 1, alpha 2, when I perform this contraction. So each contraction is a Kronecker delta. So just remember now that this contraction here means a Kronecker delta between delta and alpha 2. This contraction here means a Kronecker delta between gamma and alpha 1. And that's why we put these matrix elements in this specific form. This contraction here means a Kronecker delta of alpha 2 with beta. And finally, this one is the same as a Kronecker delta of alpha and alpha 1. So each of these contractions implies a Kronecker delta. And these are the only ones which are non-zero. And if I sum up these contractions, so if we go back to the expression here, we need now, in this expectation value, we need to take into account all possible contractions. Now, the only ones which are non-zero are those which are listed here, and the rest involves contractions between elements like that, or this one, or that one, etc. And these will all be zero by definition. So that means that what we end up with is a final result, which is alpha 1, alpha 2, of V, alpha 1, alpha 2, minus alpha 1, alpha 2, of V of alpha 2 of alpha 1, which we normally rewrote in terms of this anti-symmetrized matrix element, which runs like alpha 1, alpha 2, anti-symmetrized. And this is exactly what we got when we did the calculation with a two-particle Slater determinant. And we went through all the integrals, which gave us something which was non-zero. So it's exact, we should obviously get the same expectation value. What we are doing is actually to make a transformation to a space where we've left out the spatial degrees of freedom, but that shouldn't change the final expectation value of a quantum mechanical quantity. because quantities like the energy should be invariant under such transformations. Because if we found a smart transformations which gives us a better energy, we have cooked up something particular. Okay, so this is just an example on the application of Wick's theorem. Now you will see now that if we are going to have a free body state, four body state, and so on, this is going to call for a further simplification. And that further simplification is going to be introduced next week when we discuss what's called the particle hole formalism. So, but now you see that going back to what we did in the beginning, the first week, and also the beginning of the last week, is that this, in a way, represents a simplification of the calculational procedure. And we don't need to deal with all the spatial degrees of freedom because we can simply assume that they are encoded from the beginning. And we can just look it up, or we can calculate it if we have an efficient algorithm for doing that. So what we're going to do now after the break is actually the proof of Wick's theorem. So I think it's okay if we take a small break, even if we have this kind of mishap with the recording. So what we will do now is to, in order to prove Wick's theorem, we need a small lemma. And with that lemma, we can proceed then and prove the theorem. So there's a lemma which we introduce as a helping quantity. And what we are going to do now is to have a chain of operator, and we are going to add a new operator to that. So we have a chain of operators. Which we define as X, Y, Z to W. And then we add a new operator to this chain of operators. And we are going to make an assumption that this chain of operator has been normalized. So we are going to look at a normalized chain of operator. And the procedure is now that we need this lemma in order to prove that if Wick's theorem applies for n operators, it should also apply for n plus 1. So this is the scope of this lemma as a kind of aid in proving that if it works for n operators, it also works for n plus 1. And that is the proof by induction. And you have seen the establishment of Wick's theorem for 2 operators, 3 operators, and 4 operators. So what we will do now is to add a new operator. Let me just write this correctly here. We add a new operator. Which I'm just going to call for omega. And the lemma, what the lemma says is that by adding this operator to this normal ordered chain, I can actually rewrite this in terms of one normal ordered chain with omega plus just the set of all contractions, but involving only omega. Where this one indicates that this is a chain of contractions where we only need to include the operator omega. So this lemma is valid immediately if omega is an annihilation operator, because then the previous form which we had, this one, is already normal ordered. And if I just add an annihilation operator to a normal ordered form, then that is already fulfilled. So that means this is valid if it's valid immediately if omega is an annihilation operator. Since then, if I take n of x, y, z of w multiplied with omega is already normal ordered. And the contraction which we have to take is 0, is already normal ordered. And we know that if I take a contraction now between two operators, let's say a dagger, I, and aj, this is by definition equal to 0. So if I go back to the form which you see here, if we have an annihilation operator here among x, y, z, etc., this is automatically 0, because then I would have an ai, aj, so this is 0. But then, if one of these guys here, which is a normal order product, is a creation operator, this is also 0, that contraction which I'm making with that operator omega. Okay? So this is immediately fulfilled if that is a annihilation operator. Then we have 2 here. We assume also in all these operations, we have assumed that the sequence x, y, z up to w is normal ordered. This is a very important assumption. And if you go back to Wick's theorem, when we had it for n operators, then we had a chain of normal ordered operators. So that means that when we add an additional operator to the chain of normal ordered quantities, so if you go back to the theorem here, let's go back a little bit. So every chain which you see here is normal ordered. So adding a new operator omega here is something which is being added to a chain of normal ordered quantities. So that means that this chain has already been defined to be normal ordered. So that's why we need only to think of the addition of an operator on top of a chain of operators. So if this lemma is valid, if we can use that one, then that proves immediately Wick's theorem for n+1 operators. Because we have already made an assumption that what we are adding to is a chain of normal ordered operators. Okay? So just to remind you of that one, if this is valid, as we saw for 2, 3, and 4, everything we have here is just a chain of normal ordered operators times a contraction. A contraction gives you a Kronecker delta, gives you 0. So if you add an operator to this one, that will just take a chain of operators and add an operator to a normal ordered chain. Okay? So this is an important assumption which we are making. So what we need to think of now, so if this omega was an annihilation operator, life is pretty simple, because then it's valid immediately. So if it's a creation operator, we have to be a little bit more careful. If omega is a creation operator, that's essentially the only case we need to consider here. We need to prove the lemma if all X, Y, Z up to W are annihilation operators. So that's the only case where this can give us some problems. Since all the contractions of the type A dagger, this one, are actually equal to 0. So if we now go back to what we have here, we know that if Z here is a creation operator and I perform the contraction, that's automatically 0. So the only case which can cause problems in showing this lemma is simply now us having a chain of operators which are just annihilation operators, because that can give contractions which are non-zero. This term which you see here comes by default because I have a normal order chain, I add a new operator, and then I just normal order that one, plus all the possible contractions. So if I do that, what I get now is the last point here. So if we take this point 3, what we do then is that we anti-commute this operator gamma through all the X, Y, C operators, X, Y, C to W operators. And then what we get then, and then we get the first term, which is the normal order product. So that means the first term would be this one, just a normal ordering of that one. And then gets the first term of all, and all the anti-commutations which are then produced give the second term of the lemma. So, and, all the anti-commutations and we're going to look at an example of that. So, and all the anti-commutations which are produced when we shift the operator gives the second term, give the second term of the lemma. So what we are doing, if you now think of the application of the anti-commutation rules, in order to get this one in a normal ordered form, we actually perform the anti-commutation. So this chain is already normal ordered. So the only thing we need to do now is actually to bring this into a normal ordered form. So you can then take the operator here and you have a normal order term, but then you need to perform all the contractions with the other operators, the anti-commutations. And that is provided by this term here. So let's take a look at some simple examples just to see that this is the case. So this last term, or this last statement here, in a way, is the final proof of the lemma. To convince you a little bit, we can now look at some examples. When you have proven this lemma, then Wick's theorem follows from that, because all the terms which we have are normal order terms, and the only thing we do is to add a new operator to that. So that means that if the lemma is valid, then Wick's theorem follows from that. So let's take a look at some simpler examples here. And let's look at the case where we now have a sequence of operators. So let's look at an example of this 3 and 4. this term 3 and 4. So one example would obviously be, so what it would look like is something like this. So I would have a A1, A2, up to some AN. So we have N operators. And then I would add either an AL dagger, or I have a chain. So if this is given by a set of annihilation operators, then what I will have then, if I have an annihilation operator here, this is automatically fulfilled because that will be normal ordered. So the only case we need to think of is that if AL is an creation operator, and all the chain of operators, which is normal ordered, is actually given by a set of annihilation operators. So if I now look at the following example, suppose I have just only one operator. So let's say that n is equal to 1. Then what I have is n, normal ordered with A1, and I add AL dagger. And this is something I can immediately rewrite as the normal ordered term of A1, AL dagger, like this, plus the contractions. And when we set off the quantities here, what we have would be minus 0. Oh, that's the first term. I would have AL. This is normal ordered. So I'm changing the creation and annihilation operators with each other. And then we have 0 and plus the contraction between A1, AL dagger. So we can easily show, and I'm not going to do that because it's actually not that difficult. You can actually easily show that this applies for 2 operators, for 3 operators, etc. It's actually, if you just repeat these exercises, you will quickly see that this is the case. So I took n equal to 1 of just plain laziness because it's easy to show in the lecture. But you can see immediately that this is easy to extend. Is easy to extend to a case with n larger than 1 and a situation where you now have the normal order product where you're adding this term A1, A2, and these are annihilation operators. That's the only case you need to consider. It's actually easy to show that this is the case, but just taking simple examples. So you can generalize this one easily to a case with such a quantity of operators, which is normalized. You can multiply with a new operator, an annihilation operator to the left here, from the left. And then you can easily show that the kind of operations you lead to obey that lemma. So it's not that difficult to show. So I'm not going to say more about that. The thing I wanted to say something about is also something which is called Wick's generalized theorem, which I will just state. So let me just bring back that one. Where did I put that one? Yeah, so let me, after this, I just wanted to mention Wick's generalized theorem. And Wick's generalized theorem says that an arbitrary product, let's just emphasize it. So that says that an arbitrary product of creation and annihilation operators in which some operators are already in a normal ordered form, that has a specific expression for an expectation value. So an arbitrary product of creation and annihilation operators. So I'm just going to state that one without a proof of annihilation operators, in which some operators are already in a normal ordered form. Already in a normal ordered form is given by, and let me just set up the expectation values, which you are going to get now. So if we now are looking at a quantity like this, so when I write this now, everything which you see here is assumed to be a vacuum-to-vacuum expectation value. So I'm suppressing in the corners here this expression. So when you see everything here, it's actually a set of operators acting on a vacuum state, and then we make a transition from that new state back to the vacuum state. So we are always looking in this set of expressions into either a vacuum expectation value, or in general just an expectation value, or a transition probability, where we go from one state to the other one. So when you see this set of operations, so here we have a chain of operators which are normal ordered. We have a new chain of operators which is normal ordered. So we are calculating an expectation value of that. So we have a B1, B2, and then we have a new chain of C1, C2, etc. Now, if you think back to the expectation value we calculated before the break, so then just to remind you of what we had, so we had a state alpha 1, alpha 2. So you could think of this one as an example, which is then equal to 0 of A alpha 2, A alpha 1. So this term here is normal ordered, because we have only annihilation operators, but you could say this is normal ordered. So this is normal ordered. In this case, we have only one set of operators, an annihilation operator. When you then look at this term, in the example which we had the two-body operator, which was an A alpha, A beta, A delta, A gamma. So if you look at that chain, this is also normal ordered, because you have all the creation operators to the left and the annihilation operators to the right. And then what we had as an example here, we actually had this A alpha 1 dagger, A alpha 2. We would also call that one for a normal order chain of operators, because now we have only creation operators. So you could think of each one of these as chains of operators which are already normal ordered. And what Wick's general theorem says then is that this quantity which you see here is then given by the normal ordered term of A1, A2, B1, B2, and then C1, C2, etc. And this is automagically equal to 0. And then the next one is the set of all contractions, and I write this as all contractions of the normal order product of A1, A2, B1, B2, and then C1, C2, but where all these guys are contracted, but not within themselves, but among the sets of normal ordered operators. And remember again that when we looked at this specific terms here in the previous lecture, we know that by definition, this one is 0, this one is 0, and this one is 0, and that one is 0. So all contractions within a normal ordered operators are automatically 0. And that's why we don't need to list them, right? Unless you love collecting zeros again, right? So if that is a hobby of yours, I mean, feel free to not use a generalized theorem. It's going to waste a lot of time, of your time. So the generalized theorem says that if you have such a chain of operators, then you simply need to look at contractions between the sets of chains. Okay, so that simplifies calculations considerably. And the example which we looked at before the break was just an example of that. Okay, so in the exercises next week, we're also going to look at further examples. And it's always useful to get started with some practicing. So the thing I wanted to say something about now is actually an even more compact notation, which you will encounter in many textbooks, like the textbook of Shavit and Bartlett, which we are using, uses a diagrammatic expression or diagrammatic notation. So let's take a look at that one and introduce some basic elements. Diagrammatic. So if we look at this contraction which we have, so this is an A alpha with an A alpha dagger like this. This is something which we would diagrammatically portray as a straight line. And we would often write it like this. So we put an index alpha here. So you're entering with a state alpha, and then you destroy a state alpha. So sometimes people put a sign like this to indicate that this is a result of a contraction. But the way you could think of this is that you have a state alpha which enters, and then you destroy that state alpha. And this is often indicated by a line. So what we are going to say now is that an arrow pointing up represents what we call a state, which has been added on top of the vacuum. And since we have the true vacuum now, we can think of this as a particle which is being added. So this represents a particle state on top of the vacuum. On top of the true vacuum, 0. And in this specific case now, we have that all states are particle states. And next week, we are going to introduce a more compact notation where we will change the definition of the vacuum. We will have a new reference vacuum. And then we are going to introduce a notation which is widely used in essentially all fields of many body physics applications: condensed matter physics, material science, quantum chemistry, nuclear physics. In particle physics, these will often represent antiparticles when we introduce whole states next week. So all states now, when we use the true vacuum, are particle states. So we add a particle on top of the vacuum state. So when we next week are going to introduce a new reference vacuum, then we will actually introduce a new notation, and then we will have downgoing arrows. And the downgoing arrows are going to represent so-called whole states. So this gives us a kind of compact notation by which we are going to represent specific operators and specific states. And often you can, by this kind of diagrammatic approach, you can give a kind of physical interpretation to different expectation values. And with the diagrams, you can often, in just a simple picture, you can encode a lot of complicated physics. So let's bring further definitions here. So we're going to define a one-body operator. And let's look at an example here. And this is the interaction operator, which we discussed in terms of the energy. So we have this integral, and now we haven't assumed that these states, alpha and beta, are eigenstates of H0 multiplied with A alpha of A beta. So the way we can think of this now, this specific operator is in the following way. So we would typically draw this, so we have an incoming state beta. So you could now think of this beta coming in. Then there is some kind of interaction which takes place. In this particular case, it could be an external potential plus kinetic energy. And it's common to just indicate this one with some cross here. That's a common notation. And then this particle now can get, just to give you an example, you could think of this cross here to represent a trapping potential. So you have a free electron, which due to potential differences between layers in semiconductors can be trapped in a small region. So pictorially, you could think of what is happening, that there is a potential difference, which is now reflected like this. And you have your single electron in the state beta coming in. And then after some time, it gets trapped and stays here. And then perhaps a little bit later, it can be expelled out of this trap, just to give an example. Or it can remain in the trap. So if you're measuring the state here, it could be in a given state here, it gets perturbed in the trap and moves to another state. So the way you can think of this pictorially is that you enter with a state beta, and the motion of this object gets changed, and it leaves in a state alpha. So you could think of if it's not trapped, so it doesn't need to be trapped, but you could think of this electron coming in here, and then its motion gets changed by the interaction with this potential difference in a layer in semiconductors. If you're doing nuclear physics, you could then think of a nucleus like oxygen-16, and then you have a proton coming in here, and it gets scattered, and it leaves out in a new state P prime. That's just another type of example of how you can think of this as a one-body operator. So there is some kind of effective potential which perturbs the motion or disturbs the motion of a particle, okay? And we would typically write this pictorially as an image like that. And this means that we need some notation here. So the operator, the H0, so that represents the operator. In this case, H0, or it could just be a general one-body operator where this superscript 1 stands for a one-body operator. So it could be your proton interacting with an electromagnetic field. It could be your proton or your neutron performing a beta decay. So you could think of your neutron coming in. This is a neutron, and we know that the neutron has a finite lifetime, and it decays after some time into a proton. You have an electron, and you have an anti-electron neutrino. That's another physical process, which you can see you could represent by some kind of a magic blob here, which now is given by this cross here, okay? So these are just pictorial way of representing physical processes, which often allow us to develop some kind of intuition. And then the whole thing with a diagrammatic representation is that from the diagram here, you can read off the expression. So what you would read off here from this one, you would just read off alpha, H0, or beta. And then you see now that the outgoing state is this one. So that's the outgoing. And beta here is then the incoming. Okay? So what you could think of now is that you have actually computed this specific transition probability, and the diagram now represents either an operator or a specific transition probability. So sometimes, and this can be confusing, because many authors, they would just add the arrows immediately. Some authors prefer to add the arrows only when you perform the contractions. But we are going to use that kind of notation either for the operator or for an explicit result of a calculation, where we have an initial state, and then you act, the operator acts on that initial state, and then you end in a final state. So to be a little bit clearer, so some people leave out when they draw the operators, they would just write it like this, and then they put a label beta and alpha to indicate that you have not made a contraction with an initial state and a final state. Okay? So sometimes it can be a little bit confusing. But what we are saying now is that the outgoing state, outgoing label alpha, that represents this brass state alpha, and the incoming state beta, that represents, I'm going to put like this one, represents the state beta. And now we can do the same thing with a two-body operator. So if we take a two-body, what we have then is actually a specific state, which it comes when we put a vertex here, and then another vertex. And then we'll have a line, we have a gamma here, we have a state delta, alpha, and beta. So again, these are particle states. And the way we would set this up now is that we have a state, alpha, beta, this is the outgoing. We have an incoming state, gamma and delta. And we have an interaction element in between. And this interaction is then given by these terms which you see here. That is the interaction. There's a two-particle interaction. We are mainly going to deal with non-relativistic quantum mechanics, which means that these are time-independent and instantaneous interactions. That means, from a quantum field theoretical point of view, that each vertex here contains a set of renormalized interactions to infinite order, so that you end up with a finite interaction, which you then can use in specific calculations, like the Coulomb interactions in the interaction between two electrons, or one electron and a proton, or it could be the strong force, it could be the non-relativistic electroweak interactions, etc., etc. So what we're assuming then is that this specific matrix element, which we looked at, or this specific element, alpha, beta, V, gamma, delta, is something which we now can represent with what you see here. And there is a kind of ordering. So this is the state to the left. So alpha is a state to the left, which you have here. So when you are going to draw a diagram, or somebody gives you a diagram, from the diagram, you can read off the analytical expression for the quantity you have to calculate. That's the whole idea. So instead of me giving a long list of analytical expressions, I just give you a diagram. And then we can often discuss physical processes in terms of these specific diagrams. So this is beta, and then beta is the right term in the diagram. So this is the outgoing state. And this is the incoming. And again, you see that gamma is to the left and delta to the right. So we say that we have an incoming two-body state and an outgoing two-body state. And then we have a specific ordering. So from that ordering which you see here, you can read off the analytical expression, which is this one. So these are just notations. Now, there's a lot of interesting things you can do, because you have something called graph theory, where people have actually calculated contributions to higher order, like many-body perturbation theory, looking at the symmetries which you can express with the different graphs. So there was a whole field, there is still a whole field, where you can automatize like many-body perturbation theory, where you involve these interactions in a perturbative way. So you could think of this V as being a weak interaction, and then you can use perturbation theory to calculate the effect of these interactions to higher and higher orders. And that's something where you can set up all the diagrams using graph theory. So that's a pretty powerful and useful way of doing things. So let's now look at the kind of specific states which we have. So this was the interaction term. Let's now look at a specific state. So this is point 4. So suppose we have a two-body state, alpha and beta. You can draw this in a specific way. So we could now think of this as being two states above the vacuum. And sometimes you would draw it like this, like a vacuum state, or you would just have two arrows. So you could now think of the two particles being created on top of the vacuum. It's pretty common to skip this vacuum representation and just leave it like this, and where you now would have alpha and beta. Like that. Okay? And that means that I can now draw this alpha and beta. So I would have the vacuum state here. So you could draw it like that. And then you would have the two lines coming in, alpha and beta here. The textbook by Hjorth and Bartlett applies this kind of way of doing it. But in most textbooks, one leaves out the vacuum. So if it, how to say, during the lectures and in my notations, I will normally just leave out this drawing of the vacuum and just have two arrows to indicate a state, unless it can be misunderstood. So you could then think of an expectation value in the following way. So let's keep this notation, which is used in the textbook by Hjorth and Bartlett. And now I want to calculate. So let's call this 5 here, an example of a calculation of alpha 1 and alpha 2. And then I have this one body operator. And then I have an alpha 1 and an alpha 2 here. Alpha 2. So let's do that as an example. So the way you can draw this diagrammatically now, so we have the vacuum, which I just leave like this. And then I have the states alpha 1 and alpha 2. And now I have my interaction here with the states alpha, beta, gamma, and delta. And then I have my vacuum state here. And then I have the states alpha 1 and alpha 2. So if I were to draw diagrammatically this expectation value, I would set it up like this, and then we are going to make contractions. So one of the contractions we did was actually this one, which led to a Kronecker delta alpha 1, alpha. And then what I had here was this contraction, and then I had a delta alpha 2 or beta. So you can visualize the contractions which we put up earlier. If we go back a little bit before the break, these different contractions of that expectation value is something you can set up diagrammatically. And often it's actually a way to be able to see the wood for the trees. Sometimes you can get lost in this jungle of contractions, But if you do it diagrammatically here, it's actually pretty easy to see how the contractions are done. And then one of the contractions we did was that one. And then we had a delta alpha 2 of delta. And here we had a delta alpha 1 of gamma. And that resulted, when we did the contractions, that simply resulted in this term here. Alpha 1, alpha 2, alpha 1, alpha 2. So this would then be the way we would represent the final expectation value. And then you can just go and read off the labels and look up the table and fetch the matrix element you're looking at. So all the other contractions which we had 3 other ones which gave us non-zero results. This is something which we would get by simply taking a contraction, this one with that one. We could interchange these two. And we can interchange this one with that one, or just one on the top or the bottom. So this is a very, how to say, a visual way of doing it. And by setting up the contraction this specific way, we can read off from the diagram the analytical expression. And it allows us also to develop a kind of intuition. So the way you would talk about this is 2 particles in the state alpha 1, alpha 2 interacting with each other. So some kind of magic happens. And then these 2 guys, after the magic has happened, they end in a state alpha 1, alpha 2. Alternatively, you could think of these 2 particles being in a ground state here, and then get excited to an excited state. And then the integral represents a transition probability from alpha 1, alpha 2 to perhaps a beta 1, beta 2. So the diagrams are very handy in the sense that it allows you to assign a kind of physical interpretation to the processes which take place.